दिलीप होस्ट बना दो प्लीज. Okay, good morning, everyone. I hope you can hear me clearly and can see the screen also clearly.
Yes, sir. Good
Yes, sir.
morning.
Good morning, sir.
Very
Good
good
morning.
morning, and thank you. My sincere apologies. Yesterday, I jumped two topics. One is your pressure sensor, the piezoelectric type, and the other one being the LVDT pressure sensor. And I jumped straight into proximity sensors, okay? So before we carry on with the next group of sensors, let's complete this pressure sensors. If you remember right at the beginning, I said there are certain sensors that are not practical for use on board the ship. This is one sensor. But it is asked in the orals because they want to know the principle of working. Certain things like when we did portable gas detection equipment, you remember we discussed two very obsolete portable gas detection equipment for measurement of O2. All that they want to know is the principle of working. So you need to know that, and that is why we covered those. Likewise here also, although you will never ever find this type of pressure sensor on board the ship, the principle of operation is required to be known by you. Okay, so everybody knows what is piezoelectric effect. This here is your piezoelectric crystal or piezo crystal. Okay, and some of the piezo crystals that are there, gallium phosphate, tourmaline, and we are very familiar with this one, quartz. Okay, and nowadays you don't have those quartz watches, but quartz used to be in our good old wrist watches, no? That's why they were called quartz watches. And based on that only, you were getting your wristwatch to work. Now there are become very high funda type of watches. Anyway, that's a different story. But how does this piezoelectric crystal work? It's called a piezoelectric crystal is for the very reason that it's going to develop a voltage. How does it develop a voltage? And that is what is called as the piezoelectric effect. If a piezo crystal is kept between two conducting plates, the one at the bottom you can't see, and a connection is taken and connected to a voltmeter, actually a millivolt because it's going to be a very, very small voltage. And there is force or pressure as shown by these arrows. Remember again at 90 degrees, you can see it. Okay, at 90 degrees is acting to this and at 90 degrees even from the bottom plate. When that is going to happen on the opposing phases, then this particular piezo crystal will develop a voltage. And that voltage developed is proportional, directly proportional to this pressure or force that is being enacted on its opposing phases. Let's have a look of the animation. Of course, it's going to be a very give me a moment. Okay. Right? So this is exaggerated. A crystal is not going to be so deformed, but you get the idea. When pressure is acted on opposing phases of a piezoelectric crystal, a voltage is going to be developed. Okay? Right. So that is what is a piezoelectric effect. Now, how is this going to be giving you a pressure reading? Okay, just give me a moment. Let me, yeah, you can take a screenshot of this. Actually, it should have included this. Yeah, this is a better thing. You can take a screenshot of this rather than what I asked you earlier. Take a screenshot of this. Okay. Okay, you can take a screenshot of this. And then we will discuss how this would work. And then the reason why we cannot use it on board the ship. In fact, I'll be putting that question to you once we see the operation of this. Okay. So now let's see. I'll just zoom in. Let's see this diagram. Okay. Here's that piezoelectric crystal. And it is placed between two conducting plates. This conducting plate is fixed. This one can move. It can move up and down. So whenever a force is acting on this being fixed against an insulating base, there is an equal and opposite force also acting. Okay. And here's your piezoelectric crystal. So whenever a force is acting on it, this piezoelectric crystal will develop an output voltage corresponding to whatever the pressure is acting on this plate at the top. This plate is connected to a connecting rod, a physical connecting rod, which in turn is connected to a flexible diaphragm. This flexible diaphragm can go from this particular position, which is the normal position, it can get depressed, isn't it? How much is going to get depressed will depend on the force or pressure that is acting on this diaphragm at 90 degrees. We already saw that. Pressure per unit area, but it should be at a right angle of 90 degrees, not any other angle. So how much is this force or pressure acting on this diaphragm? That diaphragm is going to be depressed inwards. And when that diaphragm is going to be depressed inwards, obviously with this physical connector, it is going to be pressing onto this particular piezo crystal. And correspondingly, you're going to get a voltage output. This voltage output is then sent to an electrical circuit where that voltage is converted to tell you what is this pressure that is acting on this particular diaphragm. It is going to be calibrated to give you a pressure of bar, MPa, PSI, whatever the calibration is, it is going to be thus calibrated accordingly. Okay, everybody clear with how this type of piezoelectric sensor, the pressure sensor, can work?
Yes, sir.
Okay, now let's say this is placed on board the ship. Do you think it will work? If so, yeah. If yes, why? If no, why? Remember, I said you'll never find this on board the ship. Okay, so I've already given you a hint. So, will this work on board the ship?
Sir, maybe because of the vibration, false reading.
Absolutely spot on. Okay, your vibration of your ships is tremendous, especially when you are in ballast. Okay, nowadays, and month end, you're called to the, usually, you're called to the bridge for signing a portage bill and other documents, right? You know how badly the bridge vibrates, especially when we are in ballast condition. Really badly. When we get into a cabin, first thing when we are signing on, we see, okay, this drawer is vibrating, the cupboard door is vibrating. Jo vibration hai, we put paper here, there, and try and silence it so that we get a decent night's sleep. Okay, lots of vibrations. So likewise, if this is going to be vibrating like this up and down, then also this will be vibrating, no? That means the voltage of this will be continuously fluctuating. And therefore, the pressure output also will be continuously fluctuating. So you cannot depend on a correct pressure thing with regard to this because of the vibrations. Okay, that is why you will never ever find this on board the ship. You will find it ashore, yes. Okay. Hope everybody is taking a screenshot of all the notes and the respective diagram. If you so wish to take a separate screenshot of this with it blown up, well and good. Otherwise, we'll next proceed to the LVDT pressure sensor. Okay. Right. LVDT pressure sensor. If you ask what is an LVDT pressure sensor, then LVDT stands for linear variable differential transformer. Okay. Sometimes the word transformer is replaced by the word transducer. Really speaking, it is not a transducer. Okay, but we will keep this transformer because we have just completed the topic of transformers. And whenever we are talking about a transformer, then Faraday's laws of electromagnetic induction play a part. Why? Because the principle of measurement is based on electromagnetic transfer. You're not having permanent magnet. So this will be more correctly electromagnetic. Okay, electromagnetic transfer. There will be changing electromagnetic lines of force, and that's how, by the induction of the voltage in certain coils, we will see how pressure can be measured accurately. So if you're asked, as I said, what is LVDT? You always expand the letters, but don't stop there. You have to give the full definition. An LVDT is an electromechanical device that produces an electrical output that is linearly proportional to the displacement of a movable core. This type of pressure sensor, if anybody has sailed on a ship that is having B and W ME engines, you have it over there in the form of a FIVA valve. Okay? FIVA. Fuel injection variable, I forget what A stands for. Okay? Not FIFA. FIFA is Football International Football Association, not this. Okay? It is FIVA. And that FIVA valve, as far as your ME engines is concerned, one part is going to be allowing you, depending on the pressure, is going to allow the fuel to be injected into the main engine unit, that particular main engine unit. And the other side, if there's pressure acting, then it is going to be opening the exhaust valve of that same unit. Okay, so the pressure that is going to be used over there is oil pressure. And it is a tremendous pressure. It is between 200 and 500 bar. Sometimes even up to 700 bar. Very high pressure. Okay. Those who have sailed on B&W ME engines with this type of engine will know what I'm talking about. Another place where this LVDT can be used is with your steering gear. I think Mobin sir is doing navigational equipment, including steering gear. Please ask him with regard to this, where and how it is used in your steering gear. It is a device in the steering gear that is going to enable to tell you where your rudder is positioned. Okay. So how it is done there, please ask Mobin sir. Okay. Right. Okay. So we've seen the definition and what is the meaning of LVDT. So let's get down to what exactly it is. Okay. Right. So please take a screenshot of this. We'll see the explanation, and then we will also see a video on how your LVDT works. Right. So we said in the beginning, LVDT stands for linear variable differential transformer. So we are using a transformer over here. A transformer, and it's not a auto transformer, it is a normal transformer. So you'll have a primary winding and a secondary winding. This here is your primary winding. And since we are talking about Faraday's laws of electromagnetic induction, it means that this primary is going to be having a changing electromagnetic field, which means this coil, the primary winding, is going to be connected to an AC source. Only then you'll get changing electromagnetic lines of force. Now, this primary winding and secondary windings, and we'll come to the secondary windings, are put within a tube. And inside the tube, you are having that core that we were talking about. When we did the transformers, we talked about the core. The core is going to be concentrating the electromagnetic lines of force from the primary to link with the secondary. In addition to that, you are having this soft iron core. This soft iron core is a movable iron core. So it can move. Now it is right in the center. It can move to the extreme right. It can move to the extreme left. Okay? As of now, it is exactly in the middle. Just give me a moment. Okay? Now coming to the secondary. Here the secondary is split into two windings. Winding 1, L1, let's call it. Winding 2, L2. But they are not two separate windings. They are one and the same winding, in the sense that when you are going to take the connection, you are going to make L1 wound in a clockwise direction. Okay, L1 is wound in the clockwise direction. The other part of this L1 is taken and then wound in an anti-clockwise direction. And then you're going to take it out. So between both these two terminals, you have your corresponding output. Okay, so your same secondary winding is split into two. One winding is wound in a clockwise direction. It's continued, and the other winding is wound in an anti-clockwise direction. And therefore, you can say that the secondary is wound as a series opposition. This one is opposing this one, and likewise, this one is opposing this one. But they are connected in series, as you can see. Okay, so let's start with when the AC voltage is applied to your primary. When the AC voltage is applied to the primary, you will have changing electromagnetic lines of force, as in a normal transformer. Because of this soft iron core and this movable soft iron core, which is shown in red, a voltage will be induced in L1 as well as L2. Mainly because of this particular soft iron core, because it is equally linking L1 and L2. So equal voltage will be induced in L1 as it would be in L2. Let's call them respectively V1 and V2. Okay. So what is the output voltage that one is going to get over here? So V total or V out, let's call it, because we are talking about the output voltage. And remember, this is wound in series opposition. So the voltages are going to oppose each other. So V out is equal to V1 minus V2 as the standard formula. So in case 1, when it is right in the middle, equal voltages but opposing voltages are induced in L1 and L2. So V out would be, let's take for example, this is 10 volts here and 10 volts there. So 10 minus 10, okay, is equal to 0 volts. When it is equal and opposite to each other, both these voltages are going to cancel out each other. So when you're going to get 0 volts output over here, When this soft iron core, the movable soft iron core is right in the middle, this is called as the null position. Okay, null position. Okay. Now let's take my pen is giving trouble. Okay, now let's take the second thing. And when you're at this null position and you're getting 0 volts, if you're going to plot it against or in a graph position, you are starting off at this particular point. Now let's take an example. When there is force and the force is acting over here, generally in your ME engine, this oil pressure is going to be acting on this in first in one direction and then in the other direction. So when force is acting on this, it will be at 90 degrees. Then this one would have come right to this portion. I'm not coloring the entire thing. Okay. It would have come exactly right over here, which means this portion over here, okay, would have moved away from L1. So now it is no longer linking L1 as much. In fact, little or nothing is linking L1. But most of this is going to be linking with L2. Okay, it is moved now from the middle position, it is moved to the extreme end. And therefore, L2 is going to be having maximum voltage, whereas L1 is going to be having minimum voltage. Okay, so let's see what V out is going to be in this case when it is at the extreme right-hand side. Okay, let's assume it is not linking L1 at all. That means V1 will be 0 volts. And let's say you're going to be linking this maximum. So from minus 10, it is gone to, let's say, minus 15 volts. Okay, so total, your V out would be minus 15 volts. Okay, because hardly anything is linking L1. It's linking with L2. Obviously, more with L2. Therefore, the voltage induced into your L2 would be more than when it was in the null position. So say minus 15 volts. In which case, you are now gone in this direction. This is the extreme, 100% in this direction. Okay. Now let's take the next, where we will be having force acting from this direction. Okay. Now, when that is going to happen, you're going to have the opposite. Okay. Whereby this particular thing is going to come right this side. Okay. And you're going to be having L2, which is not going to be linked now. Okay, this soft iron core is moved to the extreme left because of the force acting from this side now. Okay. Therefore, what would be the voltage output now? Now you're going to be linking L1 more than you're going to be linking with L2. So let's say with L2, now there is nothing being induced over here. L1 is being induced with the maximum voltage. So let's take, as we took extreme voltage on this side as 15 volts, let's take it on this side also. So 15 minus V2 will be 0 volts since this is not linking. And therefore, you're going to get plus 15 volts DC, which means in the 100% position, you're going to be having 15 volts of DC. Okay. Is everybody clear with regard to the LVDT system?
Yes, sir.
Yes, sir.
Okay. So let's see the video on this, and it'll really allow you to understand and remember it.
Explain the construction and working of LVDT. LVDT is also known as Linear Variable Differential Transducer or Transformer. It is a passive transducer which measures displacement. It consists of a primary coil wounded on a hollow cylindrical rod and is connected to the AC source. It also consists of two secondary coils having equal number of turns and is wounded on a hollow cylinder at equal distance on either side of the primary coil. The two secondary coils are connected with each other in series opposition, so that the net induced EMF of the two secondary coils becomes, we see that a movable soft iron core is placed inside a hollow cylinder. Position of this core with respect to the two secondary coils will affect the magnetic coupling between the primary and two secondary coils. Let's now understand how this LVDT works. We see that when an AC source is activated, alternating current starts flowing through the coil, due to which varying magnetic field is produced. Now, when this varying magnetic field interacts with the secondary coil, an EMF is induced in the two secondary coils. We see that initially the core is placed in such a position that equal EMF gets induced in both the coils, due to which the net EMF of the two secondary coils becomes 0. This position of the core is known as null position. Now, if we move the core towards the right, we see that the flux linking with coil S2 becomes greater than the flux linking with coil S1. As a result, the EMF induced in the coil S2 becomes greater than the EMF induced in coil S1, and the net EMF shows a negative value. Similarly, if we move the core towards the left, we see that the flux linking with coil S1 becomes greater than the flux linking with coil S2. As a result, EMF induced in coil S1 becomes greater than the EMF induced in coil S2, and the net EMF shows a positive value. Thus, LVDT uses the magnitude and polarity of the net EMF induced to measure the displacement of its core from the null position.
Okay, any queries or doubts on how this is working and how it would work in the case of your ME BMW engines? Okay, so one side, assume if it is acting in this side, you will have your fuel injected depending on how much this has gone into the right-hand side and what is the output voltage. It can be somewhere in between. It may not be exactly minus 15. It might be less. So accordingly, that much of fuel is going to be injected into your main engine unit. Okay, a precise amount is injected. And likewise, correspondingly, when it is going to be exhausted, that particular unit, then you'll be having the pressure acting from the opposite side and your exhaust valve will open and release the exhaust gas pressure. Okay.
Sir, can you explain once again applications of the LVDT?
Okay, as I said, you will find this in your BMW ME engines as a part and parcel of a FIVA valve, F-I-V-A. I forget what is A standing for, but F, I, and V, fuel injection valve, something.
Actuating, sir, valve actuating.
Actuator,
Yes, sir,
possible.
actuator.
Yeah.
Yes.
Okay, and the other place where I'm not very familiar with, but I heard it is also used in your steering gear. Not all steering gear, mind you. Okay. So that is why I had asked you to check with Mobin sir, because he's covering that topic with you, the
Okay, sir.
steering gear. Okay. Unfortunately, I had a very good video showing how this is going to be working, the fever valve. And when my computer crashed some years ago, I was unable to recover it. I could not even get it from YouTube. If I do get the thing, I will share it with you. Okay. Right. So this now covers our full pressure sensor topic. Let's now move on to a new topic. And that is flow sensors. Okay, you can take a screenshot of this. So once again, if you're asked what is a flow sensor, then this is your answer. Flow sensors are devices that are used to measure the flow rate of fluid or gas. Mostly on board our ship, we'll be having the fluid one, isn't it? To measure the flow rate of your fuel oil into your main engine, into your auxiliary engines, into your boiler. At home, yes, we will have even this one. Okay, if you have piped gas, then you have a meter, no, to measure the amount of gas you have consumed. Otherwise, how will they bill you? Yes, for the society, they will have one common meter, but that is a different a mechanical type. But yes, we will be discussing the mechanical type of flow meter. So as we saw, one of which is the mechanical type, very, very commonly found on board the ship, and differential pressure type, also sometimes found on ship. And this is to measure the flow. Let's see the mechanical type first. The mechanical type, you will be finding 99.9% every ship you go on for the freshwater generator. Till I ended my sea carrier out at sea, all the freshwater generators that I came across had a mechanical type of flow meter. You would have seen. Okay, something is turning here, there, and you're getting those numbers changing. And they're all mechanically done. I have personally never seen a digital one. But yes, you can have a digital readout. And we'll see in a video also how you'd get a digital readout. In other words, an analog movement can be changed and shown as a digital display, isn't it? You'll have to have an A to D converter. Okay, so in the mechanical type, as you can see in this photograph, it consists of two oval gears, 1, 2, with teeth. And for every revolution of these gears, a defined quantity of liquid will pass. Now, suppose this is A, it is passing in this direction, it's coming out in this direction at position B. A defined amount of liquid will be passing through this. How much will be depending on how much these particular gears are going to rotate. And of course, this is going to be coupled to a particular readout, whether it is a mechanical number readout or a digital number readout. Okay, you don't need any power to operate this because there will be positive displacement. When pressure is going to be acting in this direction with regard to the flow, so when there is more flow, there will be more pressure acting, less flow, there's going to be less thing. Accordingly, these gears will be turning faster or slow. And accordingly, you will be getting your readout of the flow from point A to point B. A defined quantity of that liquid is going to be passing through that particular mechanical flow sensor. Okay? Is everybody clear with the mechanical one?
Yes, sir.
If you're asked in the thing, where would you find it? First thing you can say, freshwater generator, sir. Any other place in the engine room? Yes, sir. For your main engine, fuel consumption. For your auxiliary engine, fuel consumption. For your boiler fuel consumption. You'll find it in these places. Okay? Right, let's see a video on this and you will be able to understand better. Okay, it's a very long video. We don't need to see the entire video. Only the appropriate part. Okay, note it will be, this is so rugged that it can last for as many as 40 years. Even the accuracy is very, very accurate and requires no power for its operation. Of course, to get the digital one, then yes, you'll have to require a battery or something like that. But otherwise, other than that, no electrical power is required.
Thanks to its simplicity and robustness, the oval gear meter is a measuring instrument for liquid flow measurement with convincing properties in terms of accuracy, repeatability, and durability. Measurement accuracies in the range of plus or minus 0.1% of measured value and a lifetime of 40 years are not uncommon. Depending on the version, the oval gear meter cover flow ranges from 0.01 liters per minute to 20,000 liters per minute in a broad viscosity range. The operation is always identical and based on the proven positive displacement principle. Only two toothed oval gears are moving in their housing. These are driven only by the liquid flow and roll on each other without any need for external energy. With each revolution of the oval wheel pair, a defined quantity of liquid is transported through the meter. The number of revolutions is an accurate measure of the flow quantity.
Okay? So it is as simple as that. Okay? The mechanical type of flow meter. Right. So now let us see the differential pressure type of flow meter. Okay. Lest you get confused, I'll tell you when to take a screenshot. Remember when we were doing the MGPS, Marine Growth Prevention System, and I spoke about having an external tank where those anodes are going to be placed. Nowadays, you're having those anodes directly placed into your particular high and low sea chest. Okay, so let me do some few modifications over here so that you don't get confused at all. Okay, HSE, high sea chest, LSE, low sea chest. Okay. And of course, you're going to have, I'll just draw it over here. You're going to have this completely filled with the sea water. Okay. This is sea water. Okay. And here, let's put both your anodes. Okay, one is a Fe anode or aluminium anode. And since the other one is copper, let's get one as close to copper as possible. Okay, this is an external MGPS tank. Now, why I'm doing all this is just to explain when we were talking about the MGPS tank, an external one at that. Remember, we said that there has to be a flow of water. Okay, this is the inlet. Okay, of your sea water. And this is treated outlet. Okay, which is going to have those positive ions of Fe so as to prevent your pipes from getting corroded, and your positive ions of copper to kill all the marine growth marine growth organisms. Okay. Now, how is this going to think? Remember, we said a sufficient amount of treated water. If you're having this external tank, a sufficient amount of treated water, assuming your high sea chest is in thing, as I said, if you remember, I said 90% of this valve will be open and 10% of this will be here. So 90% of the treated water has to go into your high sea chest so that you will not have corrosion of your seawater pipelines and there will be no marine growth. Okay. So how does one know how much water is going? If you remember, I said there is a flow meter to give you this indication. If that water is insufficient, that means there is going to be a meter attached over here. Okay. And generally, it's going to have a black needle as well as a red needle. If anybody has sailed with this type of thing, what is this needle is going to be showing how much of that flow is there. The red needle is a set point. So if your flow is insufficient, this black needle will come and make a physical contact, an electrical physical contact with the red needle. and give you the alarm to the control unit. And then that control unit sends it to the alarm monitoring system. So then when you come down, you will see that one of those things on the control unit is showing red. And then you check and you'll find that this particular flow has deteriorated. Therefore, you can adjust. Okay, the adjustment of the inlet will then therefore allow you to think. So it should not be too much where this particular thing is gone right to the extreme right, full scale. It should be a little above this particular mark so that you get the proper treated amount of water going into your IC. Provided you are having an external MGPS tank. If you're having your anodes in your high and low C chest respectively, then this whole thing is not there. Okay, next time when you go on board, just check whether you have an external tank or your anodes are directly in your high and low C chest. So if you're having an external tank for your MGPS, then you will have this type of flow meter. Now, how is this type of flow meter going to work? Remember when we were doing the differential pressure transmitter? Okay, it's going to be exactly like that. So one side, you will be having that permanent plate. And again, on the other side, you will be having a permanent plate. Okay, and in between, you're going to have that diaphragm. So this is going to act as one capacitor. This is going to act as one capacitor. And then the differential between capacitor 1 and capacitor 2, that is going to be giving you your particular flow rate. Instead of getting the capacitance, what it is going to be doing over here, that particular connection will be connected to your meter over here. And if pressure is going to be higher on one side as compared to the other side, then this particular meter will be showing you that particular flow rate. How again is that achieved? That is achieved by making one side high and the other side low. And that is, you will be putting between a flange and orifice plate. So this is an orifice plate. An orifice plate is a blank with a small hole in between. So if this orifice plate was not there, then the pressure on this side and the pressure on this side of the flange are both going to be equal. You will not be able to have a differential pressure that is going to then be converted into this flow rate. So by having this orifice plate in between, it stands to reason that if the flow is higher, then your pressure over here is going to increase as compared to the pressure on this side. So you will be having a higher pressure this side as compared to this side. So this differential is then going to be moving this particular meter more to the right or towards the left, depending on the flow. Okay? Everybody clear with the differential type of flow meter? Where you would find it? This is where you would find it in case you are having an external MGPS tank. This is a very good example. Okay, and if the examiner asks you how to think, then you can describe just now what I told you. Right? So let's see a video on how this type of flow meter works.
The fluids flowing through pipes often have completely different properties. Therefore, different principles for their measurement are required. One method is flow measurement, based on the differential pressure principle. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube. illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity, and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid.
Okay, any queries or doubts on any of these two flow sensors?
So this differential pressure type also used in auxiliary fuel line for auxiliary engine.
Where at you're talking about? Auxiliary engine where?
Fuel line, sir, to control the fuel flow.
You can have it, but you would normally be having the mechanical type. Okay, because if you're going to have fuel flowing through this, then there are chances that this orifice plate is going to get blocked. As it is with your MGPS, it does get blocked, and then you have sometimes have a problem over here. So with fuel, you can be rest assured this orifice plate is going to be blocked. Okay, so normally you will not find this for your auxiliary engine or for that matter, any of the fuel pipelines. You will have the mechanical one.
Okay, sir, got it.
Sir, we can use this in this scrubber water line, right, sir?
Scrubber what?
Scrubber water line.
Why do you need to have flow rate measured over there?
Sir, I see in some places with the scrubber pipes, they have this flow meter and all.
May not be a flow meter. You will have this thing. What is that called? I forget now. It's some time since I've left C. Because see, anyway, that pipeline that is coming into your scrubber, that is not a narrow pipeline. It is quite a big pipeline. Okay, so the flow of your thing, and that too, it is driven by a pump. Okay, and that pump is a dedicated pump for your scrubber. Maybe they will have, but then you don't need that. What you're going to have is that particular flow thing, and that is not exactly a flow meter, where you'll be having it going into your deck seal. Okay, into your deck seal, and that is only an indication of whether there is flow or not. That's all. It's not giving you a flow rate, because that is just basically a flap thing which is telling you, yes, water is going into your deck seal. But I have personally not come across a flow meter for your this thing. If there is one, then it's fine, because I feel, at least all the ships I've been on, all the tankers I've been on, they did not have any flow meter for that. Because really speaking, you don't need a flow meter for knowing what is the rate of flow into your scrubber. If you have it, then well and good.
Okay, sir.
Sir,
Now-
I've seen. Excuse
Yeah,
me,
go
sir.
ahead.
Sir,
Yeah, go ahead.
sir, I've seen this flow meter on the BWTS plant as well, sir. On one of my ships, sir, there was a for to
Yeah,
monitor the
there,
motive water.
yes.
To motive the.
Yes, there definitely you would need. When I was leaving Sea Life, it was being retrofitted on board my ship, my last ship. So I don't know much about BWTS, but yes, there is a flow meter over there. Because once again, treated water has to go and kill those marine organisms, no? When we are doing the MGPS, I had told you that even in the BWTS, you also have somewhat a similar thing, excepting there it is only killing the marine organisms. Okay, so obviously you will need to have that treated water flowing in order to kill those marine organisms. So yes, very much so. That's another place where you can give that a flow meter over there as well. Yes, I also remember it now.
Sir, what
Okay.
about our auxiliary? Means our auxiliary boiler also have DP transmitters, na? So that this is the same thing, or that thing is different, sir?
No, when I was explaining the differential pressure transmitter over there, that is with regard to the pressure of your in your boiler this thing tank. Okay, where you are having your drum, that is where you are having steam and you are having water. So when there is more steam and less water, then your LP side is going to be higher in pressure. And if there is more water and less steam, then you're going to be having a higher pressure on your high pressure. So there it is not flow. Okay, we are not talking
Okay,
about
sir.
any flow over there. We are
Okay,
talking
sir.
about
Okay, okay.
pure pressure. Here, that same principle is used in order to give you an indication of flow. So when the flow is going to be higher, it is going to be obstructed by this particular plate. So therefore, the pressure this side is obviously going to increase. If the flow is going to be less, then the amount of pressure that is going to be built up due to this orifice place is going to be less. So this high pressure will keep varying, going up or going down depending on the flow rate. Okay, and that is then going to be converted. The same principle is going to be used, no doubt. But that particular thing is then going to be fed to this particular meter to give you that reading of flow rate. Okay.
But sir, what parameter it will measure?
Say again.
Which parameter it will measure? This meter, pressure or flow?
No. That's why we're talking about differential
Meter.
pressure flow meter. We are talking about flow meters here. So what will be the flow thing? This particular meter will be calibrated in cubic centimeters, whatever the flow rate is normally calibrated in cubic meters, cubic centimeters, whatever. Okay. Let me see in one of this thing. Okay, let me see what is the flow rate for your MGPS. Just give me a moment. Okay, so let's check. Okay, it's also known as anti-fouling device. Okay, so let's check what is the flow rate. Meter cube. Okay, 15 meter cube per hour. Okay. And here you had two things because it was a tanker, as I said, because you're going to be having your particular scrubber in operation when you're discharging. So that is why cargo handling, the amount of flow should be more than when under normal seagoing condition. Okay. So I said cubic meters. Actually, it should be meter cube. Okay. Let's see if there is that this thing. Whether there is an actual diagram of that meter, flow meter. See what I'm meaning? This is that, okay, in that schematic. Okay, this was the control unit. This is the circuit diagram. Oh, so here's that differential flow meter. Okay. So as I said, this is that differential pressure transmitter, which is then converted. So one side will be high, one side will be low. And here you're going to have your meter over there. Okay, you will have these two plastic pipes coming out. These are plastic pipes. Okay. One side going to the high pressure side and one side going to the low pressure side. So here the flow is in this direction. So this side will be high pressure, this side will be low pressure. And accordingly, as I said, this here is the black needle and this here is the red needle. So it should not touch this red needle. And if it touches the red needle, the alarm is given. Okay. So this is the contact where the electrical contact goes out to the control unit. Okay, so now you have some idea. Okay, here's the terminal arrangements within that. Inside this, you have it in the normally closed position. So if it is not flowing correctly, then it goes into the normally open condition. Okay, so this contact is opened and then the alarm is given. Okay.
Okay, sir.
Any other queries or doubts? Then we can move on to.
Sir,
Yeah.
do we also use to calibrate this?
No, you don't calibrate this. What is there is there. In any case, then how are you going to calibrate it? You need to take this out and have that particular calibrator, no? Where you're going to have high and low pressure and thing. No, you don't need to calibrate this. If at all you need to get it calibrated and there is some doubt, then you have to send it a show. So in my entire C career, we have never calibrated this.
Okay, sir.
Okay. So now let's go to a new topic. And that is level sensors. Okay, you can take a screenshot of this. Now, as I mentioned right at the beginning and again in between today, certain sensors are not practical for on-board use. And one of those sensors is this type of sensor called a level sensor by means of capacitance. So it's a capacitance type of level sensor. And when we are talking about level sensors here, we are talking about our cargo tanks. Okay, so mostly we are going to be talking about ballast tanks, your tanks are on board your tankers. Okay, you're carrying cargo, so you must know how much of cargo you are carrying. And cargo that you're carrying means you're going to know, you need to know what is the level so that they can, by means of the ullage, etc., they will be able to convert everything and then know how much of cargo you're carrying. We are not talking about level in your bilges. We are not talking about level as in your water ingress system. Those are plain on-off signals. If a water in your bilges has come to a certain height, the float will make over there. So from an off condition, it's gone into the on condition, and that will give you an alarm stating, now my bilge has been filled. It's not telling you the bilge has filled 1 centimeter, 1 foot, 2 feet. No. It is just telling you water has come to a certain level over there, which could be dangerous, and then you can flood the engine room. In other words, it's telling you indirectly that some pipe or the other is leaking badly if the water has come so fast. Likewise, in your water ingress system, it is just an on-off switch where water should not be there. Now water has come over there, for whatever reason. Okay? So those are plain on-off. Water is there or water is not there. That's it. But here we are talking about cargo in our tanks. We want to know, okay, the chief officer has opened up that particular valve, cargo is filling in that tank. How much has filled in so much of time? So then he can tell the show either increase the rate or decrease the rate. If it is empty, it is at a very low level, he can tell, okay, now I've changed over the tank is empty, you can increase the rate. And whenever they are going to be right up to the top, then he will reduce the rate. He is going to know that only by knowing what is the level within the tank, cargo tank. And one of those measures of knowing what the level is by means of capacitance. And we'll see why on board the ship, this type of level sensor is not preferred. In fact, you will never find it on board your tankers at all. We are very familiar with this formula. C is equal to epsilon multiplied by A divided by D. Capacitance is equal to epsilon being the dielectric strength, A being the area between two plates of a capacitor, and D being the distance between two plates of the capacitor. Okay? So any one of these three parameters, if it is going to change, your capacitance is going to change, then that capacitance is going to go into an electric conversion circuit that is going to change capacitance into a reading that is directly proportional as far as level is concerned. As your particular level in the tank is increasing, your capacitance is going to increase, and whatever that electronic circuit is reading this increase in capacitance, that is going to be calibrated so that it will give you a reading in feet, in centimeters, maybe in meters also. And on board your ship, it will be so many meters mostly. Okay? Right. If you have taken a screenshot, we'll move forward. Right. So let's see this particular capacitance type of level sensor and why we won't be using it on board our ships. Okay, normally we require two plates, isn't it, for a capacitor? So normally one of those plates is taken as the actual sensing element. And they used to take the tank wall as the second plate. Okay, but then in tankers, you can't have current flowing through your hull. Therefore, they had revised that particular thing, and instead of having the outer wall of your particular tank as the second plate of the capacitor, they modified that the tube in which the sensing element is going to behave as the second plate. So now you're only confined to this. One plate is the sensing element itself, and the second plate is this particular tube in which the sensing element is going to remain. Now, for a capacitor, you need to have a dielectric between both the plates. The dielectric is whatever is going to be filled in this tank. Let it be water, let it be oil, let it be anything. Even the gas that you're carrying also, that is also going to have some dielectric strength. Okay? Now, when the tank is empty, what is going to be inside the tank? What is going to be filled inside the tank when the tank is empty?
Sorry, inert gas filling.
Okay, inert gas and air, no?
Yes, sir.
Okay. So assuming that this is not a cargo tank, it is your ballast tank. So there is going to be air when that ballast tank is empty. Right? So everybody knows epsilon of air is equal to 1. If the chief officer starts filling that particular ballast tank, then this thing is going to change to sea water, which is going to be greater than 1. Okay? So C is equal to epsilon multiplied by A divided by D. Epsilon is increasing, so also your capacitance is going to increase. So as the level of water is increasing in that particular ballast tank, that is also going to be filled inside this hollow of the tube, and your capacitance is going to be regularly changing. Okay, as your capacitance is changing, this is going to go into the electronics unit over here that is going to convert this change in capacitance into a reading that is going to tell you that particular level in the tank is so many feet or so many meters. Okay. So I've taken a ballast tank over here because we are dealing with seawater, and seawater is almost the same everywhere. Slight difference in your epsilon depending on which part of the world you are in. Seawater is more dense, equator side. Seawater is less dense where you go towards the northern hemisphere, towards the poles, towards the icy regions, both north and south poles. You have plenty of ice over there, so the density of your seawater will be less because of the fresh water that is being added to the seawater. Okay, but if you are going to have this on a tanker, everybody knows on tankers you load various grades of fuel, isn't it? You go to Rastunora itself and start loading, there are at least 5-6 grades of fuel over there. Sometimes you're loading as many as 3 grades. One grade I know, which was supposed to be crude oil, it was like looking like diesel oil. It was so thin. Okay. So depending on what grade of oil you are going to be loading, this epsilon will keep changing. And if you're going to use this as a level sensor for your cargo tanks, you're not going to be loading that same cargo every time into that same tank. You're going to different ports. You're depending on what the consignee wants, he'll be asking for various types of cargo. So which would mean that this electronics unit would have to be calibrated every single time you're going to load. Not possible, not physically possible, not even practically possible. So therefore, you will not have these type of level sensors as far as your tankers are concerned. Where you may have it on board a ship is, you find all these very tiny tankers, midget tankers, if you want to call them, that are generally you find in the Far East, Korea, Japan, China, tiny fellows. They may be carrying the same cargo, same type of cargo again and again, again and again. In which case, yes, they can have this because they are going to be carrying that same fuel. Maybe. But where you can certainly find this type of a level sensor, where the fuel is not going to change, is, for example, in your car or motorbike or scooter. Okay, you're going to be loading that same fuel in your tank. You're not going to be changing one time diesel, one time petrol. Okay, so that particular epsilon is going to be constant. So you'll find this type of thing over there. Okay. You will find it in your petrol pumps because the same thing over there, the petrol pump, your tank for the petrol pump will be only filled with petrol and the other tank will be filled with diesel. They are not one time going to fill the diesel in the petrol tank and the petrol in the diesel tank. They will not alternate. They will be filled diesel in that tank and that tank only and petrol in that tank or that tank only. And so you will find it in your petrol pumps also. Okay, if at all on board, as I said, if that particular tanker is dedicated to carry, those tiny tankers are dedicated to carry only that fuel and no other fuel, then yes. Otherwise, it makes no sense because every time you will have to recalibrate this, maybe even change some components. So it is a totally unpractical thing to have on board the ship. You may have it in your ballast tanks. Because seawater, if you're going to be loading only seawater, then unless you go right to the northern or extreme northern hemisphere or extreme southern hemisphere, then yes, epsilon would change a bit, but not by much. Okay?
Yes, sir.
Okay, so we'll see a video on this one, on how it works, okay? Okay, we'll not see the entire this thing. Because most of the video is showing you how a capacitor works, okay? So we don't need that, we already know how a capacitor works. So we'll take it from the time where they are explaining how it is measuring the level within a tank.
As the dielectric liquid is introduced between the electrodes of the capacitor, the capacitance changes progressively and liquid level can be determined. To measure variations in capacitance, electric energy flowing into and out of the electrodes is measured as the circuit potential is varied. A regular flow of energy is established by connecting the electrodes to an alternating current measurement circuit. The more energy flow to the electrodes, the greater the capacitance, meaning more dielectric between the electrodes. For sensor calibration, reference measurements at empty and full tank conditions must be taken. Generally, we need to know the dielectric constant of the liquid being measured to calibrate the sensor at its full condition. With the empty and full outputs established, liquid level sensing comes down to relating sensor output to these values. Capacitor plates can also be deployed as concentric tubes, with the advantage of reduced interference, as well as improvements in mechanical stiffness and robustness. Fully integrated electronics mean no external electronic units are required, as all signal processing is managed on board. Dielectric fluctuation caused by temperature variation is managed using offset values also stored within the sensor memory. These values are typically applied during factory calibration at GIL sensors. A wide range of fluids can be measured using a GIL liquid level sensor, including fuels, biofuels, diesel, and oil, and by modifying internal components, the liquid level of electrically conductive substances, such as water, can be measured.
Okay. Any queries or doubts on this type of capacitive type level sensor? So now you know why it is not practical for on-board use as far as tankers are concerned. And they mentioned it also in the video. You have to know the dielectric constant of the liquid that is going to be loaded. So if that constant is going to change around and around, as he said, you have to keep calibrating it. Not a practical thing to do. Okay. Now the next type of sensor that you're going to be discussing is the air bubbler type of level sensor. This one you might find on older ships and it is being phased out, and we'll see the reason why it is being phased out, if not already phased out. Okay. Now this air bubbler system level sensor is having a very simple arrangement, a T arrangement, as you can see. Here you will be having a 7 kg per centimeter squared normal engine room pressure that is coming here to a regulator, and this regulator will be ensuring it might be slightly higher than this 7 kg. It is adjusted such that when the tank is empty, all the air will be coming out into the empty tank. But when the tank is beginning to fill up, okay, let's say the tank is filled up till here. Okay, when the tank is filled up to here, you can see that the level within the tank is now blocking this T section over here. And when it's going to be blocking the T section, as I said, this regulator is adjusted such that no matter what the level of the liquid is in the tank, there will still be some air bubbles coming out over here. But as the tank level is increasing, what is going to happen at this particular point, for example, the back pressure that is going to be acting in this direction, let's change the color and put, okay, if this is going to be the back pressure, then as the level within the tank is going to increase, this back pressure is also going to increase. And that will be going to a local indicator, which will be having a pressure transmitter in the sense, because pressure is going to be acting on this, isn't it? So it will be a pressure transmitter. So as the level is increasing, so also would the back pressure be acting on the diaphragm of this particular indicator, and accordingly the pressure transmitter is then going to transmit that signal to a remote position, in this case your cargo control room, as to what is the level within this tank. Okay, it is as simple as that. So whatever this pressure that is acting, okay, is going to be calibrated not only here, but in your cargo control room with regards to the level in meters, feet, whatever. Okay, very simple. But why these are being phased out is, as I said, if not already phased out from your ships, simple reason. What happens if this particular T over here gets hold? Okay, if it gets hold here, depending on how big that hole is, you will have air escaping over here instead of this back pressure. So that back pressure that is now going to act because of this particular hole in this thing, that back pressure is going to be less and less with more and more holes appearing. And therefore, the indication that is given over here, plus the indication that is given at the remote position, they are going to be wrong indications. If you're going to be using it for whatever, let it be your ballast tank or for your particular thing, ballast tank, then again you can do it. But normally on board the tankers, they don't allow welding because your ballast tank is almost right next to your cargo tanks. So normally you would have to wait till the next dry dock when your ship is gas free, then all these repairs are carried out. Okay, so that is the disadvantage of this type of level sensor. And as I said, if not already phased out, you will be finding it only on the much older ships. 20-25-year-old ships, you may find this still on. And it gives innumerable problems. Where you do find it till today, and mostly you'll find it on Korean built ships, where they are using this system for your bunker tanks. Okay, and the chief engineer never ever depends on this for the same reason that that particular bunkers will be having a certain sulfur content. That sulfur will eat into this particular pipe. And in fact, all the ships that I've sailed, at least 4 ships I sailed with these things as for your bunker tanks, none of them were correct. All were giving bad readings. So you are not going to be putting your full faith in this type of thing in case it is installed on your ship. Okay, everybody clear with the air bubbler type of level sensor?
Yes, sir.
Right, so let's take the third type. First and foremost, you can take a screenshot of this. The working principle of the air bubbler type. Okay. The third type of level system, and this you find till today on board the ship. And that is the float magnet resistance type of level system. Okay, if we take in a screenshot, I will zoom in. Let's dwell on this particular diagram. Here's your cargo oil tank. Okay, and then you have this tube coming right down almost to the end of this particular tank. Okay, normally it will not go right down because you always have unpumpables over here. Okay, there is a certain amount whereby then they stop discharging, because when they start discharging and come to this level, then the pump will start sucking in all the sludge and then can add to very severe problems. Likewise, this particular pipe is not going to go all the way to the bottom because of that unpumpables, as they call it. Inside this, you are going to have an element coming right down to the bottom of this particular tube. It's a hollow tube, by the way. Okay? Around this hollow tube is going to be a float. The float is going to be donut shaped, isn't it? With a hole in the center so that it allows the float to go up and down freely on this tube. Inside the tube, you are going to have a permanent magnet. And that permanent magnet is going to be in this manner inside that donut-shaped float. So you can imagine that when this particular tank is going to be filled, this float will be going upwards when it's going to be filled and downwards when it is going to be emptied. Okay? So this float will be going in the upward direction or downward direction, depending on whether it's going to be filled or emptied. On this element inside this tube, you are going to have several groups of resistors starting right at the bottom, going all the way right up to a certain point on the or in the tank. Several groups of resistors, and each group of resistor or resistors is going to be something like this. Across each group, and I've shown it over here again, across each group of resistors, you are going to have a switch. And that switch is this reed switch. A reed switch is a device that gets magnetized and demagnetized. When it gets magnetized, then the switch closes. When it gets demagnetized, then the switch opens. And the arrangement is such that as the float is going to come upwards, it's going to come across the first group of resistors. When it comes across the first group of resistors, it's also going to encounter this particular reed switch. And remember, when a magnet is moving in a certain way, it will magnetize this also in a certain way. So suppose this is going to be north, this one will be south. So north and south will attract to each other, therefore the contact is going to be made over here. As it is moving in one direction. When it's coming in the other direction, then it demagnetizes. Because remember, when we were speaking yesterday about those residual magnetism and all that, and how that particular core got magnetized. Similarly here also, you're going to have all tiny, tiny magnets. So they're going to be arranged in such a way as the magnet is going up, that one side will be north, the other side will be south. And then that particular contact would close. Okay. So this particular contact will then get closed. When it gets closed, what is it doing? It is shorting out these resistors. And when it begins to short out resistors, through this electronics unit over here, you will get one segment in your particular CCR lit. As each group of resistors is shorted out, one by one, these LEDs will be indicated, thus giving you the level within your cargo oil tank. Okay. Now, when the thing is going to be emptied out, your cargo oil tank is going to be emptied out. Obviously, this particular float will start coming from the top downwards. It is moving in the opposite direction. When it is moving in the opposite direction, as it comes across each of these particular reed switches, it will be demagnetizing them. These switches will be opening out, and one by one, these LEDs will get extinguished. And accordingly, it is calibrated. The level, these bar LEDs will be calibrated to give you their exact level within the tank. Not exact. It's going to have a minute error. It's not going to be pinpoint accuracy. There will be a minute error, and that error is because of the placement of these particular things. Now, whenever you're going to be placing, and I have deliberately shown it here with big gaps in between. The gaps are not going to be that big. The gaps are going to be quite small. But there is a gap nonetheless between this group of resistors and this group of resistors. So that gap will result in a very minute error with regard to the level. So it is not going to be 10% foolproof. There is some error, but that error is quite small and normally neglected. Until today, you still have these on board your tankers. In K-Line, when I sailed with them, they were making use of this. On all the tankers I sailed with that company called K-Line, they had this system. So if the Japanese are going to use this system, that means it is still quite reliable. Okay, so everybody's understood the float magnet resistance type.
Sir, reed switch and a group of resistance are the same thing, na sir?
The group of resistors has a reed switch connected across this. So if this is a group of resistors, this would be the reed switch, that is this one, is going to be connected across each one of them.
Okay, sir. Okay.
Okay, they're not one and the same thing.
Okay,
One
sir.
is a resistor, one is a switch. Two different things.
Okay, sir. Thank you.
Okay. Okay, any other queries or doubts? We can move on to the next level sensor. Okay, the next type of level sensor, and that's what you will find very commonly on today's tankers. Please take a screenshot. Today, most of the vessels are having the tank radar system. Expensive to install, but gives you pinpoint accuracy with regard to the level in the tank. Okay, so in the orals, it is asked, draw and explain the various blocks with regard to your tank radar system. It is asked in the writtens hundreds of times. Orals too, it can be asked, and that is why I say what is asked in the writtens can be asked in the orals and vice versa. Okay? So we'll be seeing all these blocks. And then I'll give you a chance to take as and when the screenshots, so that it will be made easy for you to revise. So zooming in now. Keeping our attention to this particular thing, this here is your cargo oil tank. On top of each of them, you will be having this. Let's see what it would look like. Okay? We share it with you. Those on tankers will already know. For those who are not to worry, not that they're going to be asking all these questions. This would look like this. Let's see how it actually looks. Okay? This is on board a tanker. It will look something like this. Okay? Now, that particular part which I've shown like a dome over here is called the TGU. What is the TGU? TGU stands for tank gauging unit. I'll give you a chance when to take screenshots. So far, if you've taken the screenshot of the block diagram, that's fine. TGU stands for tank gauging unit. It also contains a TGE and the IG pressure sensor. As you can see from here, it has the TGE as well as the IG pressure sensor, shown here in blue. What is TGU? Big name, tank gauging unit. The tank gauging unit is nothing but this enclosure that you're seeing here. You can see some metal and then there is a cover with all bolts. This particular thing over here, this gray section over here, is enclosing this particular electronics. This enclosure is called the TGU, tank gauging unit. Big name. It's doing nothing but preventing anything from getting into that. It's not gas tight, but certainly it is watertight. And that is your TGU. This TGU also has the TGE and your pressure sensor, the IG pressure sensor, which is blue here. Here is the TGE. So what is the TGE? TGE means tank gauging electronics PCB, which converts the signals to radar signals. So electrical signals will come from your SCU. We'll see what the SCU is coming as an electrical signal here. This TGE is converting that electrical signal into a radar signal that is transmitted into your tank. It generates a very low powered radar emission. 1 microwatt per centimeter squared or less. That means it is so low that unlike your normal radar system on your bridge, that is in kilowatts. This is in microwatts. In a continuous burst, and we'll see what it is called later on. Unlike your normal radar system, which is being transmitted in pulses. So sometimes they ask you in the orals, what is the difference between your nautical radar system and your tank radar system? So the difference between your nautical and your tank radar system, number one, nautical tank radar. Nautical, high powered in kilowatts, low power, microwatts. Okay. 2, nautical radar pulses, or rather nautical radar transmission is in pulses. Your magnetron is switched on and switched off by your pulse transformer. Okay, whoever's doing your radar will be discussing that with you. So your radar transmission for your nautical radar is in pulses, whereas your tank radar system continuous. Okay. These are the differences between both these radars. You require high power for your nautical system is because from your ship's scanner, radar scanner, it has to go a long distance, some nautical miles, before it strikes a target. And then it has to come all the way back. By the time it hits the target and comes back, the strength of that signal has decreased. So it has to have sufficient power for it to reach the target and then come back as an echo. That is why you have very high power in kilowatts. Whereas in your tank radar, what is the maximum depth of that tank? 50 meters, 60 meters? What is that? That's nothing. And therefore, you don't require so much of power. Your nautical radar is transmitting in pulses is because when the transmission is going on, you are also getting your returning echo, no? Which, as I said, is going to be very weak, having traveled such a distance. And therefore, your particular nautical radar is going to be transmitting them in pulses so that your returning echo can come. It is done in such a way that your returning echo, as shown in red, comes in between the two transmission pulses. Because if it is going to be a continuous transmission, then your returning echo is going to be swamped by the powerful power of your transmitted signal. You will not get any echo there. Okay? That is the reason, and that is the differences between both these radars, the tank radar system and your nautical radar system. Okay? We will see what is this continuous system a little later when we are convening again tomorrow. Very quickly, we will see what is the SCU unit. SCU unit is this. Let me come. Okay. This here is your SCU unit, Signal Control and Communications Unit. It's also called as the level unit. SCU standing for Signal Control and Communications Unit. It's also called as the level unit. Basically, it is this unit which would be either in your cargo control room or one deck below. In that, it contains right here at the bottom all your IS barriers, intrinsically safe barriers. Here you're going to have your power supply for the entire tank radar system, not just for this. These here are your connection ports. That means from your particular TGU, TGEs, from this, all the connections are coming here. So these are several tanks, port side, starboard side. If you had center tanks, then there would be probably one here in the middle. So since there are only two sets of tanks, they have connected it in this manner. Okay, and then it is going to have the thing to a display. This here is a backup display where you can set certain parameters such as high and low level parameters. High and high also. Remember, the level that is set over here has got nothing to do with your normal high and high level system. Let's see that over here. Okay, as you can see here, here's your tank radar system. Okay, this here is your tank radar system. And this here is your high level system. Okay, it's going down to two floats. You will see two floats over here. One is your high level float, and this is your high level. The ones that your chief officer always tests, especially before going for loading. It's got nothing to do with your tank radar system. Okay. So it has a backup display, and it will be also sending it to the main display. Okay, the main display will be definitely there in your CCR. The display could be in the form of a bar graph, which is very rare. But mostly it will be this display where you will be able to see, and let me zoom in. Okay, you can see pinpoint accuracy, all these figures that are there below these tanks. It is going to be giving you pinpoint accuracy as the level is filling up or decreasing. The backup display, which was there in your SCU, can also be there either on the bridge or in the captain's cabin, and it will be generally this type of backup display. So you'll have two backup displays. One in the captain's cabin or on the bridge, and one which was there in your SCU as a small thing where you can also interact with it. The backup display in the captain's cabin and the bridge, they are not interactive. They are there only as a display. Okay. So we have seen what is TGU, what is the TGE, what is SU or level unit. The SU is also known as the level unit. We will see, we've also seen the main display stroke backup display. And we will see later on what is this continuous transmission that we are talking. Locator, everybody knows, is a dedicated computer only for cargo work, not for anything else. The chief officer will have his own computer, the cargo control room computer, for the normal work. But for the loading and discharging operations, there is a dedicated computer. In fact, it is certified accordingly. You have a certificate stating that this is the computer that you can you're authorized to use for cargo work. Okay, I'm not sure whether the flag state is the one that certifies it or the what is that other thing like DNV and NKK and so on, whether they are the ones who certify it. I think it is the flag state. Okay, so we'll continue with our discussions of this tank radar system tomorrow. Okay, so any questions, queries, doubts you have up till this point?
Sir,
Yeah.
sir, and float sensor, we are having this arm type, right? Arm type float sensor.
You're having what type of float sensor?
Arm, sir. It's like an arm, extended
Okay.
arm. That
Okay.
one we can use it for low level, high level alarms. It is the same type of float that we used that mentioned in
A,
this type.
a float
Same
sensor, a
principle.
float sensor is only used as on off. It can have only two conditions, either on or off condition, either up or down. Okay, so it's not
Yes,
going
sir.
to give you exact level. It is only telling you when it is off condition. In other words, when the float is down, that means the level is low. And when the level is high, that float has gone up, which is in the on condition. So it's only telling you one or two conditions. Either there is nothing or there is something. That's all. It's
So
not
all
telling
kind of
you.
floats are same, right? Sir?
Yes, yes. For
Okay,
your
sir.
service tank, for your bilges, whether your bilges in the engine room or in your what is that called? Steering gear, your emergency fire pump room, you have a float system over there. Sometimes, yes, you have a capacitance type where pressure is going to be acting on that diaphragm. Okay, but it's not going to be telling you what is the exact level. It's only going to tell you that level has risen to a certain extent where it should not have risen to that extent. Okay?
Okay, sir.
एक्सक्यूज मी सर
Yeah, go ahead.
सर जो हमारा ये वाला रेडार साहब होता है इसमें जो सेंसर लगे रहते हैं इसमें तीन ही सेंसर रहते हैं सर दो टेम्परेचर के एक प्रेशर का ठीक है सर
ये टैंक रेडार सिस्टम में?
हाँ जी सर
Yes.
और सर जो ये जो अपना हाई लेवल अलार्म होता है और हाई लेवल अलार्म होता है वो सर अलग डिफरेंट थिंग है ना सर उसी में आते हैं
Completely ना,
सर
मैंने अभी बताया ना कि
एक्चुअली मैं
इधर
सर
में completely different system ना.
ठीक है सर मतलब वो वाले सेंसर होते हैं वो अपने फ्लोट मैग्नेट रेजिस्टेंस टाइप होते हैं ना सर
ना, this is plain float.
ओके
जैसे मैंने अभी बताया कि if the tank level has reached here, तो
यस
ये
सर
फ्लोट ऊपर जाएगा.
हाँ जी सर
ओके, ये ऊपर जाने से वो कांटेक्ट क्लोज हो जाएगा तो आपको अलार्म मिलेगा कि हाई लेवल इज रीच्ड इन दिस टैंक. तो चीफ ऑफिसर, in fact, this should never ever think, because what is going to happen, your light is going to light and the horn is going to think, तो क्या the show system और show side क्या सोचेगा कि अरे भर गया, there will be oil spill, तो
ओके
बंद
सर
करेगा कार्गो को. Okay, so normally this is not allowed to think. The chief officer is watching very carefully what is the level, and especially when he's topping up, तो सब लोग एकदम ध्यान रहते हैं. They will be having that thing gauging unit where the guys are going to be continuously sounding, as well as he is watching in the cargo control room कि यहाँ तक नहीं पहुँचे. अगर यहाँ पहुँच गया and then it is they are still feeling, तो यहाँ तक पहुँचेगा तो definitely it will be the high level. That is a separate light will be there. Okay, and this is, as you can see, it is a different unit, completely different from your tank radar system.
ठीक है तो सर
Okay,
बस एक डाउट है छोटा सा ये जो फ्लोट मैग्नेट रेजिस्टेंस टाइप है सर फिर ये कहाँ पे यूज करते हैं हम
that is for determining the level within the tank. और
ओके
वो कंटिन्यूस है ना, मैंने बताया कि कंटिन्यूस है एकदम नीचे से, right from down
ओके
right
सर
up to the top.
ओके 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 ओके
Okay,
ओके सर
this has got thing only for measuring the level within the tank. What you just now asked was with regard to high and high level.
Okay, sir.
तो यहाँ तक even in this system we had it on board our ship. We had this system on board our ship, and here separately you had this. Okay, where you had the high level float and the high level float. तो यहाँ तक पहुंच गया तो हाई लेवल अलार्म देगा, और इधर तक पहुंच गया तो हाई लेवल देगा.
Okay, sir.
एकदम अलग है, दोनों अलग है.
Okay, sir. Okay.
Okay.
Okay, sir.
Right. Any other queries or doubts? Okay, so again tomorrow we will continue with your tank radar system. Once we finish with that, we will move on to the next type of sensors. Okay.
Okay, sir.
Yeah. So thank you very much for joining.
Thank you, sir.
Take care, and I will see you again tomorrow at 11 o'clock.
Thank you, sir. Bye bye.
Welcome.